Hello everybody. This is Bowman Sun from the University of Potsdam. Here I am presenting one of my recent works on the detailed study about the role of energetic offsets in low offset organic solar cells. Here I will show how energetic offset has affected the solar cell performance in both generation and recombination processes. And I am the first author as well as one of the corresponding authors of this work. As we know, one of the key tactics to achieve highly efficient organic solar cells is based on simultaneously increasing JSC and VOC. Since the non-fullerene acceptors, especially the Y series, come into the play, many studies have indeed reported efficient charge generation of organic solar cells with very low or even vanishing energetic offset between the donor and the acceptor. This, of course, sounds very exciting. However, if we now look back into the charge generation process, we see that here indeed we need an energetic offset to split the photogenerated excitons so that the CT states sit below the S1 state and therefore charge transfer can happen. And then we can have the free charges. In fact, some studies have already summarized a large amount of donor-acceptor combinations and pointed out that as we reduce the energetic offset, the charge generation efficiency at first stays very high, and then up to a certain point it starts dropping significantly. In my work, I would like to show in detail the role of energetic offset in both charge generation and recombination processes in these low offset systems and try to explain what exactly limit their performance. To study this, I selected three non-fullerene acceptors, so Y5, TPT10, and OIDDBR, and blend them together with the same donor, which is PM6, and then I compared the resulted systems with the very famous PM6Y6 system. From a temperature-dependent ELQY measurement, we made it to quantify the energetic offset between S1 and CT in the working devices at the donor-acceptor interface. And then we relate that to the EQE amplitudes of each system, and then we see a very good correlation between the energetic offset and the EQE amplitude. We see that reducing the energetic offset by around 100 millieV resulted in significant drop in the EQE amplitude from around 80% to 30%. This means energetic offsets indeed play a vital role in charge generation efficiency in low offset systems. Now we see that there is a huge carry loss in PM6 OIDBR, for example, when we reduce the energetic offset. But what exactly are the loss pathways? Before we delve more into this question, I would like to firstly introduce the energetic model that I'm using. Firstly, the excitons are generated in a bulk, then they can either decay in a bulk or they can diffuse to the donor-acceptor interface. There again, they can either decay or they can dissociate to form the CT states. The CT states then go to the competition between CT decay and CT dissociation, which gives the free charge. And then the free charge can either be extracted or they can bump to each other again and form CT states. In the end, the CT states can also repopulate the excitons if the energetic offset between CT and exciton is sufficiently low. Now with this energetic model, let's quantify the contribution of each loss channel in the total carry losses. For this, we need to firstly determine the theoretical limit. This is achieved by optical simulation, which takes the optical constants of the active layer and then it calculates the light distribution in each position in the active layer. Then, if we make the assumption that each generated exciton gives a free charge, then we can calculate a theoretical upper limit for the photocurrent density, which is the J photomax. Now, if we get the ratio between the actually measured photocurrent from the device at each applied bias over photomax, then we can get a gamma value, which is also field dependent, which means the ratio between the collected charges and the generated excitons. In addition, we can also get the PL quenching values based on the PLQY of the blend and the neat acceptors. Measuring the PLQY of the blend in various voltage conditions gives us PL quenching values in different bias conditions. The PLQY represents the ratio between the emitted photons and the absorbed photons. From the PLEL measurements, we find that in all these studied systems, the repopulation of excitons from the CT states have happened. Because excitons, they are way more emissive than the CT states. So it was found that the emission property of all these studied systems are dominated by the exciton contributions. Therefore, the PL quenching can be translated into the ratio between the quenched excitons and the generated excitons. The PL quenching value equal to 1, then it means that all the generated excitons are successfully quenched, and they have either formed free charge and get extracted, or they eventually recombine by the CT states. Technically, the gamma value cannot be larger than the PL quenching value because the excitons first need to dissociate in order to give the free charge. The difference between the gamma and the PL quenching value then represents to the contribution of the CT losses. Now, we can check the gamma value and the PL quenching value for PM6 TTBR in different bias conditions. Let's firstly look at the JSC condition. The gamma and the PL quenching values are almost the same. This means all the quenched excitons have successfully formed a free charge, indicating that the losses via CT is negligible. Now, when we go to a higher reverse bias, which is -5 volts, we see very interesting things. Both gamma and PL quenching values increase together to the same level, and together with TTCF generation measurements, we reached 3 very important observations. First, we have field-dependent charge generation in PM6 TTBR. Second, the field-dependent charge generation is accompanied by a field-dependent exciton dissociation efficiency. And third, the CT losses are negligible in both bias conditions. Therefore, different from the traditional picture from the Brown model, here we see a field-dependent charge generation due to field-dependent exciton dissociation yields. The exact mechanism behind this, of course, will be very important to be studied in greater detail in the future. On the other end, if we move from JSC condition to VOC condition, we see that the gamma value falls to 0. This makes sense because in VOC condition, we don't allow any charge extraction. Any generated free charge must recombine either via the CT states or via the excitons. In the meantime, we also see that the PL quenching value stays almost the same. Now, this means that there is a very big difference between the PL quenching and the gamma value. This means now significant losses are contributed by the CT losses. Therefore, we see in this system, the carry losses in charge generation and recombination are proceeded via different pathways. In generation process, the losses are more radiative and are via the excitons, and in recombination processes, the losses are more non-radiative and are preceded by the CT states. As we talked about recombination pathways during the charge recombination, we can also have a look at the recombination dynamics. Here, we use base measurement to characterize the bimolecular recombination coefficients of all the studied systems and plot them against the energetic offset between S1 and CT. We found that as we decrease the energetic offset by around 100 millieV, the K2 value increased by more than 1 order. From the last slide, we already knew that most of the recombination proceed via CT decay channel when it comes to free charge recombination. Additionally, by comparing the ELQY of the blend and the PLQY of the neat acceptors, we found that firstly, the exciton repopulation efficiency is always very small. Among all these studied systems, the highest value is only around 10%. And secondly, there is no clear relation between the S1 repopulation and the energetic offsets in these study systems. This is probably because the yield of the exciton repopulation should be the result of a more complex competition among CT repopulation, exciton dissociation, and CT decay. After all, this means that the repopulation from CT to exciton is not enough for explaining this significantly enhanced K2 values as we see here. This indicates that probably while we decrease the energetic offset, another dark loss channel apart from the CT losses is activated. In the end, we can have the following conclusions from this work. First of all, energetics at the donor-acceptor interface is detrimental to the performance of the studied systems. And the charge generation and recombination losses proceed via different pathways in these low offset systems. It's more radiative in generation and non-radiative in the recombination process. And following topics can be the key to have higher efficiency for low offset organic solar cells. Firstly, the mechanism of this low and field dependent exciton dissociation yield needs to be understood, and we also need to understand this origin of this enhanced dark recombination channel. Is it because of the triplet excitons or enhanced CT decay rate? This needs to be studied in the future. Thanks a lot.